What would happen if thousands of birds could move through the sky like a single living fluid, changing direction instantly without ever colliding, as though an invisible mind was guiding every wing beat at once? At sunset, above empty roads, frozen fields, and quiet cities, enormous clouds of starlings begin to gather, and within seconds the sky transforms into something that no longer looks biological, because the flock bends and folds like smoke underwater, flowing in synchronized waves that appear too perfect to belong to individual animals. From the ground, the movement feels impossible, because no leader can be seen, no signal can be heard, and yet every bird reacts at almost the exact same moment, creating patterns that resemble liquid turbulence, magnetic fields, and shifting storm systems rather than living creatures trying to survive another night. And for a brief moment, it becomes difficult to tell where instinct ends and where physics begins. For centuries, humans believed murmurations were directed by hidden leaders buried somewhere inside the flock. But high-speed imaging and computational tracking revealed something far stranger, because each starling is only reacting to a small number of nearby birds, usually around 7 individuals, while the larger structure emerges automatically from thousands of tiny local decisions happening simultaneously. The flock has no commander. There is no central intelligence. There is only interaction. The movement of a murmuration is an example of emergence, a phenomenon in which simple biological rules create unexpectedly complex behavior when repeated across massive populations. Each starling constantly measures 3 things at once: alignment, spacing, and reaction speed. If one bird turns slightly, nearby birds adjust their own position within fractions of a second, and those adjustments ripple outward through the flock like pressure waves moving through water. Scientists studying fluid dynamics discovered that murmurations behave mathematically, like flowing liquids poised at the edge of chaos, because the flock must remain ordered enough to avoid collapse while also remaining unpredictable, enough to confuse predators. 2. Much order would make the birds slow to react. 2. Much randomness would cause collisions. So the flock exists in a fragile, intermediate state called criticality, where information travels across the entire structure with extraordinary efficiency. In this state, a hawk entering one side of the flock can trigger movement across thousands of birds almost instantly, not because every bird sees the predator directly, but because motion itself becomes information. The flock effectively turns air into communication. And as density increases, the entire formation begins to resemble a living equation balancing cooperation against disorder in real time inside the flock. Each bird is surviving through constant correction. Their eyes process rapid visual changes while their nervous systems calculate distance, speed, and direction continuously during flight. Even a slight delay in reaction could create a chain collision capable of tearing open the structure, but collisions almost never happen. The spacing remains remarkably stable despite the extreme speed and density of movement. This efficiency reduces energy waste, improves defense against predators, and allows thousands of animals to function as though they are connected parts of a larger organism. The environment also changes around them. Large murmurations can alter local airflow patterns, creating shifting pressure zones that affect how the flock moves through the atmosphere. To predators below, the shape becomes psychologically overwhelming. Because the constantly changing mass prevents accurate targeting, the flock does not fight through force. It survives through confusion. But the deeper scientists study murmurations, the more unsettling the phenomenon becomes, because the same mathematical principles governing these birds also appear inside collapsing financial markets, neural networks, traffic systems, and human crowds during panic events. Large systems begin to move unpredictably when individuals follow simple local rules. Order slowly transforms into instability. Small disturbances spread farther than expected. One movement influences another. Then another. Until control no longer belongs to any single eventually. The system itself begins reacting faster than the individuals inside it can fully understand for millions of years. Evolution refined this behavior across changing climates, predators, and migration routes, shaping nervous systems capable of processing enormous amounts of collective information without centralized control. Today, scientists use murmurations to study artificial intelligence, swarm robotics, autonomous drones, and crowd prediction models. Future transportation systems may move using the same principles. Future machines may communicate through decentralized reactions instead of direct commands and across decades. As human societies become increasingly interconnected through networks moving at near instant speeds, the behavior of starlings may begin to resemble something uncomfortably familiar, not because humans are becoming more intelligent, but because large connected systems naturally drift toward collective behavior beyond individual awareness. Murmuration reminds us that intelligence does not always emerge from a leader, because sometimes the most powerful forms of order appear when countless small lives surrender themselves to patterns too large for any one of them to fully see. And somewhere above the fading evening sky, the flock continues moving like a single thought passing